And so finally, it seems throughout this session on assessment, we have been in one or another way talking about the involvement of peers. And so finally, we end up with a paper on peer grading and, of course, on algorithms and data structures. And please welcome Mehdi.
Thank you. Yes, so excuse my voice. I have a bit of a cold. Yes, so after these talks about automated grading, now I'm going to talk a bit about peer grading. We did this talk at the University of Hamburg, but now Ulrike is in Tübingen. I'm also in Tübingen. Morteza, he's in Hamburg. So we're a bit scattered now. Yeah, let's just start. So, thank you. Okay, so classical grading, just very quickly, I'm going over this. We have a lot of students. We have one or several teachers, TAs. I'm not only talking about MOOCs, I'm also talking about university classes, school settings, anything right now. So we have a lot of students. We have one or several TAs who grade the submissions, and that's the final scores. That's it, very simple. Now the idea of peer grading is we take these submissions, we anonymize them, we shuffle them. Each of the students, so it's the same students, gets maybe 3 submissions, grades these, and then we have, in this case, 3 grades for each submission. What do? We just take the mean, and that's the final score. And that's where this topic comes in. So instead of just taking the mean, maybe we can do something smarter. Maybe we can use a better aggregation algorithm to get more accurate scores. And we're going to talk about the meaning of accuracy here also. Yeah, so that's the setting. The big question is, how do we aggregate these scores, the grades? The second question that we try to answer is, are peer grades as accurate as TA grades? And obviously, we have a lot of challenges here. The first big challenge is that the students usually, it's the first time that they are grading other homework, so they don't have a lot of experience. The second problem is the bias. So some students might give everyone quite high grades. I know other might just be like, if there is a small mistake, you would just give very low scores to everyone. The next problem is that we only have a limited number of grades. We can't ask a student to grade 20 submissions every week. And the last problem is cheating. So in this system, students might try to cheat the system. I don't know, try to give everyone low scores, so their own score is higher maybe in comparison. Stuff like that, it's a big problem. Yeah, so our university class, we just implemented this. We took the class on algorithms and data structures. It's a class where you have some easy questions, some hard questions, like the whole range. We did it for the whole semester. We had 220 active students in the course. And over the whole semester, we collected about 14,000 grades. Something that was maybe a bit special, we didn't ask the students to solve the homework on their own, but they solved the homework in groups of 3 and also submitted them in groups of 3. But the grading, so the peer grading step, that was done by each student on their own. So you see that we get triple the amount of peer grades by doing this. Yeah, so after solving the homework, we gave the students detailed scoring rubrics, telling them exactly maybe one or several possible solutions, and also telling them how to grade them. So how many points to give for what section, basically. And overall, every submission was graded in 3 different ways simultaneously. First, we asked the students to grade their own submission. And that was the order is actually in this. So I asked them first to really grade their own submission so they can familiarize themselves with the scoring rubric and also see their own mistakes. Then we gave them the other submissions from other people. Usually every student got 2 other submissions and had to grade them. And at the same time, we had still our TAs, which did it in the classical way. They graded all submissions also. Yeah, so let's just look at one exercise. This is an example for an easy exercise. Maybe not easy to solve, but easy to grade. because here we had one exercise, there were, I think, 4 or 8 questions. So we had several questions, and every question was a yes or no, had a yes or no answer, but just crossing yes or no wasn't enough. Actually, the students had to either give a counterexample if it was wrong, or if it was true, they had to give a proof. But for every question, the student could either get 1 point or 0 points. So the grading should be easy, right? Yes, so let's just look at the histogram. So we're looking here at the histogram. So 0 point, the grade of 0 is the worst one, 1 is the best one. Looking at the TA grades, which is the red curve, we see that the peer grades are slightly higher. Okay, makes sense. Students maybe don't find mistakes, or they're just more generous to each other. But it's quite close, at least on the histogram. Looking at the self-grades, we see that they are even higher, which also makes sense because maybe students just like to give themselves more points. But if we just don't assume the students are doing that, maybe it's just harder to find mistakes in your own proof, which could also be one reason why the self-grades are higher. Yeah, so if we look at the mean absolute deviation from the TA grade, the peer grades, it's 0.8, so we could say 8% of the total score, which looks fine. I mean, it's quite small. The self-grades, only 12%, so it's not that much higher. And if you combine the peer grades and the self-grades for the whole, for each submission, it's still 8%. So it looks great. Everything looks good here. Now let's look at another exercise. Here the exercise was quite a bit tougher. The students had to design an algorithm to solve a particular problem. And not only design it, they had to prove that the algorithm is correct, and also that the algorithm meets a specific runtime. Yeah, so the problem here was we had students who submitted an algorithm, and the algorithm was actually, maybe it was correct, but it didn't meet the runtime. So for example, they had to design an algorithm which was sublinear, but actually the algorithm ran in and a half or something. So the problem was the runtime was not correct. But the problem was that a lot of students who did the mistake themselves also didn't realize that the runtime wasn't correct for the other submissions. So they just gave the full scores, although it was obviously wrong. And what you're seeing here is the TA grades. You see, it's not normally distributed anymore. So we have like half and half. So some submissions are quite bad, some submissions are better. And the peer grades, they are like off to the right. They're a lot higher. And the self grades are just extremely high, because a student that did the mistake obviously didn't know that it's wrong if the student submitted it himself. Yeah, so the mean absolute deviations, they are quite a bit higher now. On the peer grades, it's 18%, self-grades, 28%. So basically, self-grades are just, you could call it rubbish in this case. If we combine them, it's 21%, which is still not that good. And also, just on the histogram, you can see that the grades are not so accurate. Yeah, so let's just look at the scatter plot. This is a scatter plot over all submissions for the whole semester. So each point is one submission that was made. On the x-axis, you see the TA grade for that submission. On the y-axis, you see the mean peer grade for the same submission. So if all peer grades and the TA grades were the same, we would just have on this line, on the diagonal, all points would lie on the diagonal. But we see that it's quite scattered. Yeah, so we see a lot of things. So first, we see that most of the points, especially when the TA grade was low, we have the peer grades which are quite a lot higher. So for example, on the left, we see even the extreme case, we have a TA grade of 0, and we have, for example, 2 submissions where the peer grade was just full score. There's an explanation for that, actually. So for example, in some cases, when you looked into the data, you saw that the TA found that the student who solved the problem, so the solution was correct, but the TA found that the student had copied it from the internet, for example. So the TA gave it 0 points, and the peer grades, they didn't realize that, so they gave the full score. Yeah, so that's that. The overall bias, it looks quite bad in the scatter plot, but the overall bias is not that bad. So we see the peer grades only 6% on average, so 6 points actually higher than the TA grades, which seems fine. The self grades are 12% higher, or 12 points, which is also not that bad. So the bias is not the big problem. The problem is a large variance that we're dealing with here. Yeah, all in all, at least we can say this is a good base for improvements, right? So we can improve a lot, hopefully. So what did we do? We just took a probabilistic model from a paper which was released in 2013. We had to tweak it a bit to fit our setting, but mainly what we're doing here is we put some priors on the data. So first, we put a prior on the true scores. We are saying that the true scores, the actual TA grades in our case, that they are normally distributed with some mean and some sigma. Then we have a bias and reliability for each student. So every student has a bias. Bias meaning just that, for example, if a student has a bias of 0.1, it means that the students always add 0.1 to the grades, to the actual grades of the submissions. And the bias values, they are again normally distributed for the students. And the reliability grades, for the students, these are gamma distributed. And reliability is basically meaning that if a student has a high reliability, the student will usually report the actual grade, the true grade. If the reliability is 0 in the extreme case, the student would just report random grades. And now, having all this, we look at the reported scores. So we say that the reported scores are normally distributed again. We take the true score. So every student takes his true score, adds his own bias, and then we have the precision, which is given by the inverse reliability of the students. Yeah, so we want to estimate, so we have the reported scores only. So the first line is all we have, and we want to estimate the other 3 lines. We take the expectation maximization algorithm for that, and we estimate the true scores, bias, and reliability at the same time from the data. Yes, we tested this on artificial data on a lot of different data sets. It works quite well. I can maybe show you a plot later if you have enough time. So that's that. And now maybe the next question is, why did we choose this model? Why not another model? There are a few other models, but mainly this model is good because it's simple in a way, and also it's very natural. So the choices are quite natural. I mean, we have a bias for each student, usually reliability. It all makes sense in a way. And the other the other algorithms which exist, they make similar assumptions usually. We always have some notion of bias. We always have some notion of reliability. So it's quite similar. Yeah, and now let's just look at our data and the results. So we have 4 different algorithms. First, we take the mean score. That's the yellow one. Then we have the median score. And then the blue ones are the same model that I just introduced. Single task means that we train the model on every task separately and estimate the scores. Multitask means that after the whole semester was done, so at the very end, we take the whole data set from the whole semester and we estimate the bias and the reliability values for each student. And the assumption is that every student, for example, the bias, it's not variable, it's fixed, right? So a student which is overall generous with the scores will always give higher scores, and reliability the same. Yeah, so if you look at it, we have box plots. We have 3 different groups. On the first groups, you see the data, the results on the self-grades, then on the peer grades, and self and peer grades combined. And these box plots are given over the mean error of every task. And what we're seeing basically, the summary is that no model doesn't really improve over mean. We see that the errors are not really lower. Sometimes they're a bit higher, sometimes a bit lower, but in general, it doesn't really improve a lot. Yeah, so maybe actually what I forgot to mention is that we took the L2 error, so it's like the squared error. So maybe the next point is that we don't really care about the actual grades. We care more about getting the order right. So for example, if one submission is better than the next one, so that's more important than actually, I mean, maybe that's more important than getting the actual grades right. So we look at that. We take the Kendall-Tau correlation. It's a bit different than one we saw earlier. But it just measures the similarity of 2 rankings, basically, for each task. And here again, we see it doesn't really improve. That's just the quick message. Yeah, so the big question is why? why don't the models work? Because in the paper where the model was actually introduced, they got good results. Okay, obviously, on artificial data set, it also worked quite well, but in our case, it doesn't really work. So let's just try to find an explanation for this. The first point is maybe we don't have enough data. Maybe the data is just too small. Recall that we have 6 peer grades for each assignment. We tried the same with 15 peer grades for each assignment, and we got the same results. And actually, you can't really get more, right? You can't ask students. I mean, in our case, even 6 peer grades is quite a lot. You can't, because we had groups, so every student actually only had to grade 2 submissions. But in the normal case, you would have to ask every student to grade 6 or more papers as submissions, and that's not really practical. The next thing is that maybe we don't have enough data to really estimate the bias and reliability of the students. But then again, we took the multi-task model and we estimated the bias and reliability over the whole semester, and still it didn't work. Maybe the next problem, so next explanation, is that we are using the wrong priors. Because obviously, remember that I said we are making the assumption that the true grades are normally distributed. But as we saw earlier, they are not really normally distributed, right? For example, here, if we take the TA grades as the true grades, they are obviously not normally distributed. It's like a bimodal distribution somehow. But the thing is, that's not really a problem. So we tried other priors, we tried a uniform prior. It doesn't change a thing, basically. The next thing, maybe we have just too many unmotivated students, so the peer grades are just crap. And if you have random grades, basically, in the worst case, then any model couldn't really improve over the mean. We looked into the data again, and we saw that we only had very, very low number of students who, for example, really reported random scores, for example. And actually, when we have those, when you have only a small number of those, the models should be able to give them low reliabilities and give them a lower weight for the final score. And actually, the models should improve from them. The next thing is we had a lot of different assignments. We had some assignments which were easy. We have some assignments which are quite hard. So maybe mixing them together and trying to estimate the bias and reliability for all different kinds of assignments is not a good idea. So we tried the same, but this time we grouped the assignments. We just took the easy assignments where actually the errors were low anyway. But still, the models couldn't really improve over mean. The next possible criticism is that we're using the TAs as baseline. So we're assuming that the TA grades are the true grades, which is natural to assume, but maybe it's not a good idea to do this. And the next problem is we had not one TA, we had 6 different TAs, which again could maybe grade differently. So we checked it, and we saw that the TAs, usually they graded quite similarly. So the difference was quite small between the different TAs. And just to confirm it, we also took the artificial models and we added, so we did everything as before. But what we did was, when we wanted to calculate the error on the true grades, which are given by the TAs usually, we added some noise. And then we checked if the model can cope with that. And then, yes, the difference was maybe a bit smaller between the mean algorithm and the models, but still there was a big difference even when we added a lot of noise. So that's using different TAs couldn't really explain that we couldn't improve over mean. Mm-hmm. Now for the last 2 points, and these are the points that we think are the problem. So the first problem is bias versus reliability. As we saw, the bias is not really a problem in the data set. It's a large variance that we have. And the problem is that this model actually, if you look, for example, at the artificial data or also in the original paper where the model was used, we saw that the model improves over mean because it corrects for the bias. But correcting for the reliability, so correcting for this variance that we have in the data, that's actually something that the model cannot really cope with. So it tries to, obviously, but it's very hard because first problem, if you just compare it. So we look at two different settings. First, we have the setting where every student reports the actual true grade plus some kind of bias. If you look at this setting, so there's no reliability. Every student just adds their own bias and that's it. If you look at this setting and just assume that we know these bias values, and we can just subtract them and that's it, right? So the error will be 0. But if you do the same with the reliability, meaning every student has some kind of variance, some student might always report the true grade, another student might just have a larger variance. Even if we know these variance values, even if we know the sigmas, we will still not have an error of 0 because it's probabilistic, right? We can only maybe improve it by giving students who have a low variance a higher weight, but still the error will be above 0. So that's mainly the first problem. And the second problem is that the biggest sources of error is not really given by this bias and reliability, but it's given by just lack of knowledge. So for example, in the case where we saw that the students simply couldn't find the error, where the runtime of the algorithm wasn't correct, that's something that you cannot really correct with some kind of model like this. Yeah, so the conclusion, we saw that the models fail to improve over the mean estimator. We talked about the main reason that we don't have a lot of bias in the data. The sources of errors are different. And the reliability, which is the big problem, it's just hard to model that and to estimate the values. Now I have two questions maybe. The first question is, maybe the model is just too simple. Maybe we can just introduce like a more complicated model, a model which can detect cases where a student just totally reported a random grade or something. If we can come up with a more complicated model which can maybe improve over mean with 10% accuracy or something, would it be acceptable for the students? That's the first question. Because if a student doesn't really at some point understand why I'm getting this grade, for example, with this model, okay, it does make sense. But if the model is more complicated, that we lose some transparency, and maybe that's not a good idea to do that. And the next question that we tried to answer was that is peer grading viable option for large university classes where we simply don't have enough TAs? And the question, the answer in this case is maybe it's not a good idea to use it in this kind of setting, algorithms and data structures. Maybe with another setting, another classroom where you write essays, maybe it's a good idea to use it there. Yeah, and last but not least, the data set that we collected, it's available on the website. I think you can see it on the bottom right. You can download it, you can try your own algorithm on it, and just see the results. Thank you.
Thanks very much, and we still have time for a few questions. Before we go to questions, I want to remind the speakers there's forms over here to fill out for the video permission, so please do that afterwards. Okay, let's go back here. John, we'll get you second.
Hi, Renee Kazolchet from Stanford. It's great to see replications, even if they fail. I think there was a recent educational research article that said there are only 0.13% of articles that are published are replications in education. So we should strive to get that percentage to be higher. I've actually looked at that first question about are complicated models acceptable for students? Because I think it raises an interesting human factors question, right? If we have these fancy models, and it seems the way forward to cleverly combine the grades that are being given, how do you explain this to students, right? And especially looking at trust, because it's a peer grading. You need to trust what is going on in the system. You need to trust your peers, and so it's an important question. And what I did was an experiment, looking at so one of Chris Pischer's models of peer grading, and either telling students nothing about how this grade came about, telling them procedural information about what was happening and how they arrived at that grade. And in addition to that, a third condition where they also got the details of the different outcomes, what they would have gotten before or after. And the interesting outcome there was that students indeed lost trust in the system if they were not given any information or if they were given too much information. But just the procedural explanation, we're doing this because it's fairer, it makes the grades more accurate, that reinstilled trust. And so that might be a way forward as we move toward more complex models, if we feel confident enough to say that it is fairer, it is more accurate.
Yes.
Hi, John from Stanford. Let me tell you a little bit about the course that the work that you cited by Chris Peach and others was based on. So this was a Scott Clemmer's HCI course, which is a design-based course. One of the things that Scott realized, some time ago, maybe a decade ago, when he was just doing this as a regular on-campus in-person course, he was very highly regarded as a teacher, but his lowest rating was about fairness in grading. And so he decided at that point that really to teach a design course, it's important to emphasize evaluation of designs. So the subject matter of the course moved into substantially evaluating designs and doing kind of a review of others' designs as part of the explicit subject matter of the course. So my point is, and the question I have, is that the course was really aimed at part in content on the educational value of peer evaluation and setting criteria and helping students think about that. So I think that, my hypothesis is that that's an important factor. It's not really on your list. My question is whether you covered that in any sense in your course. I think it would make sense in a data structures and algorithm analysis course to tell students they will be reading code written by others and they'll have to do things like efficiency analysis about it. So how did you approach that in the course and what's your thought on that?
That's a good point, actually. So I also talked with Chris about this. In the original course, so one experiment which was actually done by the Stanford group was that they had some submissions which were gathered by just a lot of students, a huge number of students, and they took that, the mean grade of those, of the big number of students, and they compared that to the TA grades, TAs in a way, and they gave those to the professor of the course and had the professor say which of these grades look more correct. And the result was that the professor found the mean grade of a large number of students actually to be more accurate than the grade given by just a single TA. And in that sense, I think peer grading does really, it's more fair, as you said. But in our setting, so that's where I think there's a big difference. So in our setting, you can't really say, so even if you ask 200 students and you give them some solution, and maybe 150 of them say it's correct, full grade, and another 50 say maybe it's not correct, the mean grade will not be more accurate than the grade that one TA gave. Because here I think in an HCI course, it's more about an opinion, and if you take the mean of a lot of students, you get a higher fairness, actually. But in our setting, the one TA, usually it's just the knowledge which matters. So if you take one TA, usually the result will still be more accurate than the average peer grade of even the whole class, maybe.
Chase Geigel, UAC. I was curious, I don't know if it was mentioned in the presentation. If it was, I missed it. What are the questions that you're asking on the rubrics of the students? I'm trying to get at, how hard was it for a student to answer one of those questions reliably?
So you mean on the scoring rubric?
Yeah, what did the rubric look like? What were the kinds of things that they were evaluating?
For example, when the task was to create an algorithm to solve some particular problem with some specific runtime, for example, the scoring rubric, it just gave one or several, so the most natural kind of examples. So we gave them one solution or maybe two solutions. We told them what to look out for, what mistakes to look out for. We tried to, for example, tell them this kind of solution is not correct, but obviously it didn't always work because it's hard to really know this beforehand. Yeah, so mainly does that answer your question? Or? Yeah. Okay.
have one more question, and I think we'll close for lunch. Just what your thoughts?
So I'm thinking through I'm Justin Reich, I'm from MIT. I'm thinking through the implications of this, and it sounds like one of the things that you're saying is that peer grading is less likely to be successful in places in which either there is a more definite right answer, or there is narrower, or there's like how much of this would this be a useful proxy to determine whether or not peer grading is useful under circumstances in which variance in TA grades is very low? Peer grading is likely to be inferior to TA grading, and in circumstances where TA grading has a bunch of variance, those are the circumstances under which peer grading is likely to be similar to or better than TA grading. That might correlate almost perfectly with whether something is sort of subjectively graded or objectively graded or something like that, but maybe it doesn't. But the way I frame it around variance means that there's some sort of like, conceivably some way of having a quantitative measure that you use to predict whether or not peer grading is appropriate in a circumstance. Does that seem like a reasonable line of investigation to look to further investigate as a consequence of your study? Or would you how would you frame that kind of thing differently?
Yeah, so I think, so the way you phrased it, actually, it sounds reasonable. So if, for example, on essays, I think the TA grades would have a large variance. And in that case, I think peer grading would make more sense. And we would have to get a more fair result. I'm not sure if in cases like this, where the TAs would agree on the same solution, if peer grading would always fail in this sense. I think in this case, the biggest problem was that even giving the students a good detailed scoring rubric, even then, still we have a lot of students who just get it totally wrong, so who get a bad algorithm and just don't find a mistake in it. I think that's a bigger problem. So if the TAs can't agree on it, maybe peer grading is more fair, but if the TAs agree, it doesn't really mean that peer grading doesn't work, it just, in some cases, it's like this. Okay.
Okay, well, thank you. And thank you to